This one is the first of a few videos we have recorded with the aim of introducing you to the fundamentals of one of the most important instruments for an electronics engineer, the spectrum analyzer. Let us start with the basic concepts. A spectrum analyzer is essentially an instrument able to measure the individual frequency components that make up a complex signal. Former analyzers were designed to measure steady-state or repetitive signals, but today you can find a family of instruments able to measure spectra of pulses and transients at very high speeds, as well as to provide information not only on the amplitude of the frequency components but also on the phase. The input stage of a typical spectrum analyzer is essentially a subsystem which contains user-selectable amplifiers and attenuators, as well as some filters. All spectrum analyzers make use of a frequency down conversion process. This is mainly due to the fact that you always need to digitize the signal, and the analog to digital conversion is much easier when you work at low frequencies. The frequency at the output of the down conversion subsystem is usually called intermediate frequency. This stage actually represents a complex circuit in which one can find several mixing stages. Depending on the frequency band, the instrument might need to do an up conversion first and then a down conversion to reduce the effect of parasitic harmonics generated by the mixers. The analyzer has an IF gain compensation circuit that comes after the down conversion block. Its main function is to compensate mixer losses. The circuit block you will find after the gain compensation is the one that has experienced major technology improvements during the last years. It is in charge of doing the analog to digital conversion and signal processing, and has made possible to significantly reduce the measurement time and lower the minimum frequency of operation. In order to understand how a modern spectrum analyzer works, it is necessary to revise first the operation principles of a classical spectrum analyzer. This instrument is usually called superheterodyne spectrum analyzer because the frequencies at the output of the down converter are always above the audio frequencies. Let us assume that you want to build an instrument able to plot in real time the spectrum of a signal, just magnitude, as a function of the frequency. This will be the display. A ramp generator can produce a triangular train of pulses, and therefore can give us a voltage that is proportional to time. You can imagine what would happen if we make an arrangement like this one. We apply the ramp generator to the horizontal axis of our display and a constant voltage to the vertical axis. We just plot a point in the screen that has the coordinates given by the voltages at both axes. Since the vertical voltage is constant and the horizontal one is proportional to time, we obtain a horizontal line in the display. And if we apply a sinusoid, we will see something like this. We can now keep the voltage at y-axis and apply another triangular pulse to the x-axis. Doing this, we will repeat the waveform in the display and therefore obtain a stable visualization of our signal. Good, we have built an oscilloscope, but this was not our objective. We want to convert the x-axis into frequency. And this is the hat trick we need. A voltage-controlled oscillator is able to produce an output frequency proportional to the input voltage. Therefore, if we use a VCO in the down conversion subsystem that is controlled by the ramp generator, we obtain an intermediate frequency at the output that is proportional to the time. This can be used to make the sweep in the x-axis equivalent to a sweeping frequency. Well, it seems that we have all we need. Now let us check if this works. Maybe the easiest way is to follow the same approach than before. We started by applying a constant voltage as a function of time. The equivalent in the frequency domain would be just white noise, for instance, thermal noise. We know that the spectrum of this noise is constant, so we just connect at the input a passive load at room temperature, and we see a horizontal line in the display. Nice, but if we try to measure a sinusoid, we will find the problem Remember that in our oscilloscope we were applying to the vertical scale a voltage that was continuously changing with time. This allowed us to build up the time dependence on the display while sweeping the x-axis. But now we are in the frequency domain, and therefore when we try to measure a sinusoid we are actually applying a signal that has always the same amplitude. We want to draw in the display a Dirac delta at the proper x coordinate, but we simply cannot do it with this arrangement. We need something else. Basically what we need is to remove these two parts of the plot. And this is the solution. We insert a selective bandpass filter at a fixed IF frequency that will allow us to see in the display the peak we are looking for. This filter is called a resolution bandwidth filter. Okay, now it's working, but we can still do a nice improvement to this configuration. The classical spectrum analyzer includes a last stage called video stage that is very helpful to detect weak stationary signals above the instrument noise floor. It is essentially a detector and a low-pass filter. This block allows the user to effectively smooth the trace. Unfortunately, it will not reduce the noise floor as well. Anyway, now our spectrum analyzer is complete.